Let's start. Okay. So today we will continue our discussion on dynamic matching, and we will give a different algorithm that will be a deterministic algorithm. Okay. So let me just state the result that we will see today. And this. And this is the paper. Okay. So as far as the result is concerned, the point is that this is a deterministic algorithm. So yesterday we saw a randomized algorithm, and more importantly, more important than the result, we will now see the application of two new techniques which we have not seen before. So just recall what are the techniques we have covered. Just one is the principle of monotonicity, and the second one is random sampling. So all the results we have covered so far were just some sophisticated applications of these two techniques. This class we are going to see two new techniques, and these are not standard names. I am just naming them, but there is nothing specific in a name. It is more important that you get the main idea. One technique what I call is sparsification, and the second one is periodic rebuilding. So what is sparsification? Let us just try to see this in the context of a matching problem. So we know that suppose our just goal is to maintain some constant approximate matching. So we know that dynamic matching is easy on bounded degree graphs. So what do we mean by easy? Suppose you have a graph with maximum degree d, then how much time will you need to maintain a maximal matching in this graph? Order d time, right? Insertion will take constant time. For deletion, you just traverse to the adjacency list of the endpoints of the edges that get deleted, and it's order d time. So this is good as long as d is small, but the point is that in general d can be large. So what is a very natural thing to ask? Given a graph, does it always admit a subgraph of small degree that roughly preserves the value of the approximately maximum matching? So let us just say that opt of G is the size of the maximum matching in G, and the question is does there exist a subgraph G prime of G such that two conditions are satisfied? A, the maximum degree in G prime is small, and condition 2 is, how will opt of G prime relate to opt of G? It is going to be at most opt of G, right? So, because you are considering a subgraph, so we know this for sure, because any matching in G prime is a valid matching in G, but in addition we want this guarantee. So, what does this mean? It means G prime approximately preserves the size of the maximum matching. Okay. And let us call such a subgraph a kernel. This is just a technical term which I will be using. Okay. Okay, let's just think about it. I'll come back to your question. Let's just parameterize this. Maximum degree in G prime, suppose is D, and then I am going to call this thing a D kernel. Okay. So now I am going to come back to your question, but let's first continue for 2 more minutes. What is the point of doing this? The point is, suppose I give you a subroutine that maintains a D kernel in a dynamic graph efficiently. Then you can run your trivial maximal matching algorithm on the D kernel to solve the problem, right? So, basically the algorithm will consist of 2 steps. The first step will be you are getting a graph G, and now you feed it into a dynamic algorithm that say maintain D kernel, and this will pop out a different graph G prime that satisfies these 2 conditions, and then you feed it into a different algorithm that says maintain maximal matching, and this pops out a matching M prime in G, and this is your output. And the update time for this subroutine is going to be order D, and what we are going to show is that you can maintain a D kernel in order n over D update time. Okay, and hence the total update time will become order D. So, if you just set D to be root n, the total update time becomes square root n. Okay. So, now let us just start with some very basic observations. Why is this technique I am calling sparsification? Because you are just maintaining a sparser subgraph with fewer edges, and then you are running your favorite algorithm on this sparser subgraph, and the point is that a dynamic algorithm intuitively will be faster if you run it on a sparser subgraph. Okay. So, this is why it is called sparsification. The second thing is this maintaining a D kernel. You see, the update time here increases as D's value drops. So, if D is very large, this update time is very efficient, right. Now, this has an intuitive feel to it. Why? Because if D is very large, say if D is n, what will be a D kernel? The entire graph, and this update time will become constant. Okay. On the other hand, suppose D is 1, D is 1, very small, then what will be a D kernel? It will be a matching. Maximum degree of a node is 1, right. So, if D is 1, this D kernel will become a matching, and then this condition implies that this kernel is a matching, and this condition will imply that it will be an approximate matching. So, if D is very small, then basically you are not gaining anything, you have to solve the entire problem here. So, there is a trade off here. If D is very large, this part is easy, but maintaining a maximal matching on the kernel is hard. On the other hand, if D is small, then this part is very hard. On the other hand, maintaining a maximal matching on the kernel is easy. So, there is a trade off, and it seems if you want to balance these two terms, you have to set D to be root n, and you get this. Okay. So, now to come back to your question about what does a D kernel look like. You are asking something about spanning for subgraph. Not necessarily, right. Suppose there is just an isolated edge somewhere and there is a huge giant component, and you can leave out that isolated edge, right. You are just going to lose one edge in your matching, and so what I mean is that suppose there is a very dense graph here with many edges. Suppose there is just one tiny isolated edge here. You can very well leave aside this edge in your kernel. I mean, you can just say this is my kernel. Yeah, then you cannot leave many of these edges, but it's not necessarily going to be a spanning subgraph. Okay.
Wanted to output the matching that you get in G, or you can leave those edges and later you can pick up those edges in your matching M prime.
M prime, the edges in M prime belong to G, right?
I mean, if there are those kind of isolated edges which are actually, you can include them in matching.
Oh, so the point is that it depends on what algorithm you have. The algorithm that I will propose will not have these isolated edges. All I said was that it's hypothetically plausible that you have an algorithm that has these isolated edges. Okay. Now, you might want to include them, might not, but the point is that if you just care about constant approximation, you need not, right, because M prime already gives you constant approximation. Clear? Okay. So, now the point is, what will be a good candidate for maintaining a D kernel? What do you think? Do you have any suggestion? Spanning tree. Okay, let's consider that example. Suppose you have a complete graph, okay, and suppose I give you a spanning tree that just looks like this. It's just one node and it's just adjacent to all the other nodes. Will this be a good candidate for a D kernel? No, because the maximum matching size here is 1. Okay. So, it turns out I am just going to define a notation, something called a D matching.
But then don't we need the degree condition? So that does not satisfy the degree condition, right? Suppose you are able to maintain some forest where degree condition is satisfied.
Okay. So, we are going to ultimately maintain a D kernel where D is root n, right? So, just consider root n such stars. So, then the approximation guarantee will become root n. Okay. So, what is a D matching? A D matching is simply a set of edges E prime such that the degree of every node among E prime is at most D. So, this is a generalization of matching, right, because what is a matching? A matching is a one matching. Okay. And now we can also think of a maximal D matching. What is a maximal D matching? Just like a maximal matching, no further edge can be added to it. So, this is a subset of edges E prime such that if you look at any unmatched edge u v in then either this is already equal to D or the other endpoint's degree is already equal to D. Again, if D equal to 1, you just get back maximal matching. Okay. So, now what we are going to show is that for every D in 1 to n, a maximal D matching is a D kernel. Okay. What is the proof? Let us take any maximal D matching. Let us say this is E prime, and let us partition the set of nodes into two subsets, tight and slack. So, what are the tight nodes? The tight nodes are denoted by T. By definition, these are those nodes whose degree is exactly equal to D. And what are the slack nodes? The remaining ones whose degrees are strictly less than D. So, now let us just look at this picture. This is tight nodes, this is slack nodes, and the edges that are in the kernel, I am just drawing them like bold edges, and the edges that are not in the kernel, I will draw them like a dotted edges like this. Okay. So, the first question is, can there be any dotted edge between two nodes u and v that are slack? No, right? Because by definition then this will not be a maximal D matching. You could have added this edge to the matching and it will still be feasible. So, basically you know that all the edges between two slack nodes are within the kernel. So, the dotted edges, they are either crossing these two sets, this can happen, or they can be between two tight nodes. So, there can be a dotted edge like this. So, this is the picture you should have in mind. Okay. So, now there are two cases. Let us just look at the optimum matching. So, M star is the optimum matching in G. So, either say half fraction of M star is coming from the edges in S, in which case those edges are already present in the kernel, and hence the kernel preserves the value of the maximum matching within a factor of half. Is this argument clear? So, case 1 is if you just take the intersection of the matched edges and the set of edges whose both endpoints are S, E of S. Suppose this is greater than say half times M star. If this is the case, then just look at this. this is actually a matching in the kernel G prime whose size is at least half times the maximum matching in opt. So, you are done. What is the more difficult case? The more difficult case is that half fraction of the match stages in opt are incident upon the tight nodes. So, let me erase this part.
What is the value of alpha we are aiming at?
Any constant will be fine. So, we will be getting probably 4 using this argument that we are going to make. Okay. So, the second option is let us say E of t is the set of edges in E that are incident upon the tight nodes T, and the case now that we are looking at is this is greater than okay. Now, can you see that in this case we can retrieve a constant fraction of the match stages from the kernel edges, and why? See, the question is how many match stages incident upon the tight nodes can there be? It can be at most the number of tight nodes, right? Because one tight node can contribute at most one match stage. So, if we can, so that means that the number of tight nodes is at least half times the size of the optimum matching. So, what we will show is there exists a matching M prime in the kernel that matches a constant fraction of the tight nodes. If we can show that, then just compare this size of this matching M prime. It is going to be at least a constant times t, and hence at least a constant times the size of opt. Now, can we show this, that there exists a matching M prime that matches a constant fraction of the nodes in T? What will be the greedy way to construct a matching M prime? Anyone? Exactly. Pick any edge that is incident upon T, and then what you do? Just delete all its neighboring edges that neighbors on their endpoints, because you cannot pick those neighboring edges any further. So, the algorithm is pick any edge UV these are the edges in the kernel that are incident upon T, and then delete all the incident edges upon U and V, all the incident kernel edges upon U and V. So, this is step 1, this is step 2, step 3 is repeat. Till there are no more edges left. So, So, how many edges will you pick? The edges that you pick will form a matching, right? That is going to be your matching M prime. So, how many edges will you pick? Sorry? Mod T edges, right? Why? No, you need a lower bound on this, right? You need to say that you are going to pick at least a constant fraction of tight nodes. Okay, why is that?
Either all your edges are empty
Mm-hmm.
or your edges are twist. So if all your matched
Okay, so M star
in
as L, so M star intersection ET
Mm-hmm.
is at least half of M star, right? So all these edges are incident to T. So
Mhm.
if we randomly pick any edge, this edge can kill at most 2 other matched edges. So
Not two other, right?
at most, right? So for every, so in the worst case, for every 2 edge in M star, we get 1 edge from the greedy angle.
In E prime will T form a deregular graph?
Yeah, okay. So, all that you are saying are in the right direction. So, I think there are slight bugs in each of these claims. So, I am just going to give you a different proof, but what you said, I think that can also be made into a correct proof. Okay. The argument is this: when I say delete all the incident edges, incident kernel edges that are incident upon U and V, how many such edges can there be? At most 2D, right? Because each of U and V has at most D edges in the kernel. So, by doing this, you are just deleting 2D edges at most. So, what you know is that for every edge that you match, you delete at most 2D edges. And initially, what was the size of the edges, size of this set? Size of the kernel edges that are incident upon T?
Size of T times T.
By 2. Why? Because size of T times D is the sum of the degrees of the tight nodes, and now some edges might be counted twice because both their endpoints might be tight. So, the total number of edges incident upon tight nodes is at least T times D by 2. Okay. And now, just look at this algorithm. You have a bucket of these many edges. Now, what this algorithm does is, it is matching one edge and just deleting 2D edges from this bucket. Again it is matching one edge and it is deleting 2D edges from this bucket till the bucket becomes empty. So, for the bucket to become empty, by a simple counting argument, how many edges do you need to match? For each matched edge, you are deleting 2D. So, the number of matched edges will be at least this divided by 2D, right? And what does this mean? This is mod T over 4. So, this way you are constructing a matching in the kernel whose size is at least 1/4 of the number of tight nodes, which means it is at least 1/8 of the size of the optimum matching. Hence, in this case also the kernel preserves this approximately the size of the optimum matching. Here alpha turns out to be 8, but with more sophisticated analysis you can show that this is actually going to be 2. Okay, but we are not going to get into that far. Sorry? Why?
So what is my goal? I want to pick edges from I want to pick matched edges from T, right? So
Suppose the worst case situation in this argument will be, what if all these edges are between tight nodes? Okay. Then size of E prime of T, the number of edges incident upon the tight nodes, will become exactly T times D by 2, right? Okay. And then if you just look at this matching, you are matching one edge and then you are unmatching, I mean then you are just deleting 2D edges for every matching.
Seems like if I don't follow this algorithm, the deleting 2D edges,
Mhm.
if you have T, if your both the endpoints of your matched edges are in T,
Mm-hmm.
for all the matched edges,
Mm-hmm.
how many matched edges you can get? Not T by 2, right?
No, this is going to give you a maximal matching, right? How many matched edges will you get? You are saying, okay.
I'm not talking about this algorithm. If there are, if both the endpoints of the matched edges are in T,
Mm-hmm.
then how many matched edges you can get in T? Mod T by 2.
So actually,
Why are you saying this?
example where this is not true. So the
Right.
intuitionism is
Fine.
Yeah, I don't see why that will be true. Okay, but okay, later on we will see that at least this can be made to be 3. So we will see an alternate proof which will say that a D kernel here will be a 3 approximation to the optimum matching using a different proof. Okay. So now this is how we maintain it. Thing. So we want to maintain this D kernel in a dynamic setting. What is the problem with that? Again, if a non-kernel, just look at this picture. If suppose that edge insertion takes place, what will you do? If that edge insertion is incident upon a tight node, you do not need to do anything, right? This is already tight. If both the endpoints of the edge to be inserted are slack, then you have to match it and then some of the endpoints can become tight. If a non-kernel edge is deleted, there is nothing you need to do. If a kernel edge is deleted whose both endpoints are slack, then again there is nothing you need to do, because all the slack edges are already kernel edges. So, the only issue is when a kernel edge is deleted, that is incident upon a tight node. Okay. But if such a thing happens, the degree of a tight node actually in the original graph can be as large as n, right. So, this guy was tight and now I deleted one of these edges, say. So, now its kernel degree becomes d minus 1. So, you need to check if you can find one other edge incident upon it to include in the kernel, but to do that naively again you need to traverse all its neighbors, right. So, how can you improve the bound? This seems that this will again become order n, because the maximum degree of a tight node is n. But I am claiming not this exact setting, in a similar setting you can maintain in order n by d update time. And this is where we will see the application of the next technique that I just mentioned, the concept of periodic rebuilding. So, what we will do is we will consider a notion of an approximate kernel. What is an approximate D kernel? You just relax the concept of tight nodes. So, again you have partitioned the nodes into slack and tight as before. So, these are the tight nodes, these are the slack nodes, and suppose this kernel is E prime. So, now what was the guarantee that you had? the guarantee was the degree, the kernel degree of a tight node is exactly equal to D. Now, I am going to say, suppose it is between D by 2 and D within a constant factor of D for all tight nodes. And for slack nodes, the condition remains exactly the same as before. So, the degree of its match degree of a slack node is at most D, and finally, you have this condition that if you see an edge in the original graph whose both endpoints are slack, then this edge must be part of the kernel.
Stack and title means partition.
Yeah. No. Okay. Yeah. So, what I am saying is that now suppose I give you a partition of the nodes into slack and tight that just satisfy these three conditions. Okay. And just compare this setup with this. What is the difference? These two conditions remain exactly the same, that every slack node has degree at most D, and if there is an edge between two slack nodes, that edge is part of the kernel. This is exactly the same as before. The only thing that I changed here is that here we had the constraint that a tight node had degree exactly D. Now, I am just saying that a tight node has degree between D by 2 and D. So, now the point is that given this kernel edges, there might be multiple partitions that satisfy this property. That is correct, but you just fix one partition. Okay. So, now the point is you can show that this will also be a constant, this will be a valid D kernel, meaning that this will approximately preserve the size of the matching. And why is that? It's because again look at the maximum matching in the original graph. If a sufficient portion of it is coming from edges whose both endpoints are slack, that is preserved here in this kernel. Again look at the second case, that most of the edges in the maximum matching in the original graph are incident upon the tight nodes. Then just look at the greedy algorithm for computing a matching in the kernel that we considered. What will change? The only thing that will change is that you start initially with a bucket of now T times D over 4 edges. Why? Because there are T nodes and each node has kernel degree at least D by 2. So, it is T D by 2, and now you might be overcounting some edges. So, you again divide it by 4. 2. So, you have a bucket of T times D by 4 edges, and now what you are doing again the same thing, right? You are just picking one kernel edge, matching it, and then deleting all the edges incident upon its endpoints. And when you are doing that, for every matched edge, you are deleting again at most 2D edges. So, then the size of the matching in the kernel that you will get is again at least T by 8, which is within a constant factor of opt. It is exactly the same argument. Okay. Now, the point is that what do we gain by doing this, and this is where this principle of periodic rebuilding comes into picture. What do we gain? Since we intuitively feel that the insertion only case is easy for dynamic matching, let us just focus on the decremental setting. How will you maintain this structure in the decremental setting? So, suppose you start with a graph and initially you start with an exact kernel like this. So, there all the tight nodes have degree exactly D, and now the edges are getting deleted one after the other. When a non-kernel edge gets deleted, you do not need to do anything. When a kernel edge gets deleted with both endpoint being slack, you do not need to do anything. The point is The interesting case is when a kernel edge gets deleted whose one endpoint is tight.
So then you can allow d by 2
Exactly.
on expectation.
Exactly, not in expectation, in an amortized sense. Expectation means randomization. So, exactly. So, the point is this: what will happen if an matched edge gets deleted that is incident upon the tight node? Not a matched edge, a kernel edge gets deleted that is incident upon the tight node. After a while, its kernel degree will drop below d over 2, right? Then it can no longer remain as it is. You need to decide whether it is to become slack and go down, or whether it can again become tight. So, what will you do? Suppose this node V is now critical in the sense that its degree is exactly d by 2. You traverse through its adjacency list, the entire adjacency list, and for every other endpoint that you find. So, suppose you find that this is an edge in the adjacency list, not a kernel edge. Just ask yourself, can we match? Can we include this edge in the kernel? How can we include this edge in the kernel? If the kernel degree of W is strictly less than D, W is tight here, right? Then of course we can include it. W remains tight. What is the other option? The other option is W is here, and again just check if the match degree of W is strictly less than B. If yes, just add it, and then in this case the point is that W earlier was slack and now it might become tight. Now its match degree can become exactly B. So, W will go up, okay, and this way you can find out the new status of V. So, at the end of this, V will either become slack or it will remain tight. So, if V remains tight, it means after this swipe, so you are just swiping through this entire neighborhood.
We look at the neighborhood
In the original graph, yes, because the kernel edges are already there, they are not going to help you anymore, right. So, you just swipe through V's entire neighborhood in the original graph and deal with each edge and try to match as many edges as possible. At the end of this swipe, if you see that degree, kernel degree of V is now exactly equal to D, V remains tight, otherwise it becomes slack and goes down. So, what is the work that you did for this? Total work order n, right?
How many edges do you have?
It depends on what you see in this neighborhood list.
You're only looking at these neighbors, right?
Yeah.
So how do you match the edges?
So, you
You're
found
picking an edge from the edges emanating from V or somewhere else.
no, I do not understand your question. First of
If
all,
you pick an edge,
no, first of all you are not matching that edge, you are deciding whether to include that into your kernel.
Building the matching.
The building the matching is here, we have not yet come to that. I am just saying that which edge to pick in the kernel.
so how do you decide what to pick?
So, just look at all the cases, right. So, you are considering a node, an edge V W. You ask yourself right now, is V's kernel degree equal to D? If yes, there is no question of including it, right, you can just skip it. Otherwise, V's kernel degree is less than D, then check if W's kernel degree is equal to D. If yes, there is no question of including this in the kernel. The interesting case is when both these two degrees, the kernel, when both their kernel degrees, sorry, they are strictly less than D, then you include this edge in the kernel and their kernel degrees, each of them increases. The only thing is that now you might need to update W status. So, if W was already tight here, it does not matter, W was earlier satisfying this invariant, it was satisfying this invariant, might be tight, right.
Because you have
Yeah, because the tight nodes are not now exactly tight, they are approximately tight. So, if W is tight, then you do not need to do anything. If W is slack, then you just check if now after this insertion of this edge into the kernel, if W's kernel degree is becoming equal to D. And if it is becoming equal to D, then what you would say? You say that W now becomes tight and you just put W here. Okay. So, now what is the amount of work you are doing? You are doing constant amount of work per edge in the original graph, that is incident upon V. So, the total work you have done for this is order n. Is there any question?
Can you please repeat the argument and ask about
Mm-hmm.
the first thing that you said, right? That for V and W.
Mm-hmm.
So is that edge that edge you're searching for, right? So above that you said that degree of V in E prime and degree of W in E prime both are less than D,
Mm-hmm.
right? So why can W can also be in T, right? Because suppose degree.
Yeah, W can also be in T, right? The point is that you just you just insert into kernel as many edges as you can incident upon V, okay, and then you just finish this scan and then see what is the kernel degree of V. If at the end of this scan the kernel degree of V is less than D, V becomes slack, otherwise V remains tight. So, now it requires constant work, right, and after you have done this work all these invariants are again satisfied, right. This requires order n work and after this scan all these invariants are again satisfied. So, then what is the amortized update time? You are still doing order n, but where have you saved?
So we started with degree exactly D.
Exactly. So, that is the point. So, if you just look at a node, you can just partition its lifetime into phases. So, a tight phase is when the node remains tight. So, a phase is just a contiguous time interval during which it either remains tight or it becomes slack. So, if you just look at a node V and suppose this is the time step and this is the node V. So, it just looks like this. So, suppose this is a tight phase, then you have a slack phase. Then again you have a tight phase, and then again you might have a slack phase. They will by definition alternate. There cannot be two consecutive tight phases, right, because then they will be merged into one. Now, the point is that at the beginning of every tight phase, the degree of this guy is exactly T. No, not T, D. And when the tight phase ends, its degree is D by 2. So, during this phase, at least D by 2 edges incident upon V must have been deleted from the graph. So, although you are doing order n work on this phase, you can for this phase lasts for at least D by 2 edge deletions incident upon V. So, on V the amount of work you are doing is the amortized amount of work on V is order n by D. Now, you might ask that okay, we are arguing only about the tight phase, what about the slack phase? The point is that when it becomes slack, so the point is that the moment this node goes from one set to another, depending on the data structure, the worst thing that can happen is it might need to inform all its neighbors that it has now gone to the other set. That is the worst thing that can happen, but that will require again at most order n time, right. because you are just informing all its neighbors. So, in the worst case, you are spending at most order n time in the beginning of a slack phase and also at the end of a slack phase. But these two times can be subsumed into this order n time you are spending on this tight phase, right. So, the way to think about it is the phases alternate for a node, it is tight slack, tight slack, tight slack and so on, and at each transition you are doing order n amount of work. And then the thing is, this means all this order n amount of work you can charge to all the tight phases, and then the amortized work that you are doing is order n by d. Yeah.
If when the degree becomes less than d by 2,
Mhm.
you are adding the edges.
Mhm.
If your degree now becomes more than d by 2 but less than d,
You become slack, you come down here, and then during this slack phase you are just doing constant work, right, per edge insertion deletion. And then when will this slack phase end? When the degree becomes exactly equal to d, then again at most you do any work, but the point is that you just charge this O(n) work to these tight phases, it does not matter. Okay. Now, why is this called periodic rebuilding? It's basically you just have a structure, and for a long time you are absolutely doing nothing. I mean, you are doing virtually very little work. I mean, the structure is distributed here, the structure is per node. Each node has to maintain some properties, and the properties are set up in such a way that we have sufficient slack, so that we do not need to do much work on this node for a long period of time, and then at the end you just recompute everything from scratch. At least for this node, this is what we are doing. We are recomputing this structure for this node from scratch. Okay. And we will see again multiple examples of this idea later on in the course. Okay. So, now let us just look back at this framework. We have seen how to get a D kernel, that is a constant approximation. We have seen how to maintain a D kernel in order n by d time, and we know that we can maintain a maximal matching in a bounded degree graph in order d time. Now, is this the whole of the proof, or do we need to do something more? I claim that there is one part that is left out, it is not very important, but still there is something missing in the argument. Meaning that just from this picture you cannot conclude that the total update time will be order n by d plus d. See, the point is this, just look at this subroutine. It has order d update time per edge insertion deletion in G prime, not per edge insertion deletion in G. So, when we are talking about update time, we are talking about per edge insertion deletion in G. So, you have to ensure that in this picture, if there are T edge insertion deletions in G, there will be order T edge insertion deletions in G prime. If this thing blows up, then you cannot say that the total update time is n by d plus d. But can you say that? If I give in the amortized sense, of course, because in the worst case, see, the point is the moment this node was tight and it is now kernel degree becomes d by 2, that happens, that is triggered by the deletion of a single edge in the original graph, right. But after that single edge deletions, in the worst case you can insert d by 2 edges in the kernel. So, but on average, can we say something? On average, this ratio is still constant, right, because you start, look at the beginning of a tight phase. In the beginning of a tight phase, this guy's kernel degree was d, then it dropped to d by 2. So, that means there were d by 2 edge deletions in the original graph, during which you did nothing on the kernel. And then at the end of this transition, in the worst case, you are again inserting at most d by 2 edges, right. So, on average, per edge insertion deletion in G causes constantly many edge insertion deletions in G prime. Is this clear?
there is something like at most order D.
That is bad for us. We need the following guarantee that in the sufficiently long run, if you insert delete t edges in G, there will be ordered t edges inserted deleted in G prime.
What is T here?
T is, what did I say? In the long run, suppose for sufficiently large T, if you insert delete T edges, just fix any T, 1000, 2000 something. If you insert those many edges in G, the number of edge insertion deletions in G prime can be off by at most a constant factor. Now, is this true in the amortized sense? That is what I am asking. Can you see why this is true in the amortized sense? It's because when is the case that you see a bunch of edge insertion deletions in G prime? It's when a node V was tight and now its kernel degree has dropped below D by 2. And how many edge insertions are taking place? At most D by 2 or at most D. But for this to happen, prior to this, at least D by 2 edges must have been deleted from the original graph. Okay. And one last thing, I made a minor mistake, I just realized it right now. The tight and slack phases will not actually alternate. I mean, there can be two subsequent tight phases, because it might be that a node is tight initially, then its degree, kernel degree drops below D by 2. Then you fix it and in the end you find that now its kernel degree is again D. So, that will be the beginning of a new tight phase, right. So, initially